There is only one student. So we can start now.
Yes, sir, please start. You're live now.
Okay. Okay. Good afternoon, friends. Uh, this is Accelerator Physics course. It actually officially it is 30 lectures or 12 weeks course, but we gave some extra lectures and we gave 36 lectures. Out of that, two lectures were of great interest not only to our country but the world over. That is on ADS, Accelerator Driven Subcritical System, and that is 36, lecture number 36. So that will come at the end. Now this course is given in three modules. First one is DC accelerators, second is linear accelerators, and the third one is cyclic accelerators. And the other two colleagues, they are still working. I have superannuated, so they will be available only during that period. Rest of the time they are in office. So what we have done is that we will have three interactive courses, sessions, and in that sessions we will try to clarify the doubts, and if anything you want to know about accelerators, we will try to tell that also. So this is the first one. First one is on DC accelerators. Although DC accelerators, the energy is low, but they are still very useful today. Accelerators of TeV range are also available. They are have been operating, and in the case of DC accelerators, the energies are maximum energy is few hundred MeV, but they are still very very useful. One should not think that since the energy is very low, so DC accelerators are not useful. They are still useful because the energy resolution in DC accelerators can be very high, and therefore some of the experiments or studies which require very high resolution, they can be studied only through DC accelerators. So you will find that almost in all the labs, big labs, DC accelerators are also there apart from the high energy cyclic or linear accelerators. Highest energy so far is in TeV range, and they have been operating at several labs now. Accelerators both for proton, electrons, heavy ions, particles and antiparticles have been built and they are in operation, and therefore they are very useful. And nowadays accelerators are also used very extensive medical field, health for healthcare, particularly for uh, cancer diagnostics as well as therapy. And therefore these accelerators are now increasing in number, particularly in hospitals. Nowadays, most of the hospitals are having uh, accelerators which produce isotopes used for diagnostics as well as treatment of cancer and other diseases. So in this interactive sessions, we'll have three interactive sessions, one each for the each module. Today we will be talking about DC accelerators, and will be uh, clarifying or answering all the questions regarding DC accelerators, and the remaining two will be dealt with the linear accelerators as well as cyclic linear accelerators are called linex. Cyclic accelerators, they consist of cyclotrons, betatrons, and synchrotrons, colliding rings, and all that. And Dr. Amlendu Sharma will answer the questions on that. So today, I think anything which you need for DC accelerators can be clarified if there is any doubt left. Now, at this place, I would like to, before anybody asks, I would like to make edits which I am, or rather, clarify the error which we have made while that. One was that, for example, Cockcroft-Walton accelerators, they are very low energy accelerators, and they were used for many applications, particularly for reactions which is D falling on the deuterium beam falling on the D target, and DT reactions. Now the Q value, so reaction is D plus D is equal to helium 3 plus neutron plus Q value, and Q value which I mentioned in that lecture was 2.7 MeV. Then later on I checked with several experiments. The 2.7 MeV was mentioned in one of the papers. That is why I wrote that. But later on, I found that internationally the Q value which has been accepted is about 3.27 or about 3.3 MeV. So that is the correction, that internationally accepted Q value for the D plus D is equal to going to helium 3 plus neutron particle. The Q value for that reaction is about 3.27, or you can say roughly about 3.3. There are several experiments have been done for that, and the values quoted by them are varying from 2.7 to 3.5 or something like. Average value has been taken to be, most of the experiments are showing 3 point, about 3.3, and the value which is accepted is around that 3.3 MeV. Some experiment have shown 3.27 also. So that was one correction. And other correction was that in the case of Van de Graaff accelerator, for example, the high voltage terminal is not connected to the pressure vessel. So the line which is shown by the uh, solid line is not correct. So from terminal to pressure vessel, there will not be any line. There is no metallic connection of high voltage terminal to the pressure vessel, and that correction has to be done. I think somewhere in the write up we have made that correction. And an earlier interactive session I have told that, and we have shown all the figures also, indicating that there is no correction in that, so that line has to be removed from there. So these were two edits in the lecture, first one. And since the Van de Graaff thing was appearing in first three lectures or something, so everywhere that correction has to be made. Uh, of course, the people who have not worked with Van de Graaff, they will not be able to realize that. But I realize that correction is needed. One should not think because high voltage cannot be connected. High voltage terminal cannot be connected to pressure vessel, which is grounded. Because if that is the case, then the voltage will not increase, and therefore there is no metallic connection between high voltage terminal and the pressure vessel. So these were two corrections which have to be. Now, in this case, there were about 8 lectures, and 2 lectures were later on. So, if there is any doubt regarding that, I will be very happy to answer that. What I understand is that in India now, there are almost 30 to 40 accelerators are adding every year, particularly in hospitals and for isotope production. Isotopes are used for both diagnostics of various diseases as well as for their treatment. So this field is going to be very important, and as well as new, another new field which is coming up now, where accelerators are going to play very important really role is ADS, accelerator driven subcritical system, which is used for nuclear energy production using thorium, and that is very important for Indian perspective, because India is having very large amount of thorium. We don't have that much uranium, which is used in the present reactors. But if we can use thorium in the reactors for energy production, then it is estimated that we have so much thorium that at least for 500 years, roughly 500 years, we will not have any problem of nuclear fuel for the reactors. The difference between the reactors for thorium utilization is that in the case of this ADS, reactor operates with K effective of less than 1. That is means it is not critical, it is subcritical, and that is one reason why it is very safe. It is considered very safe because there is no problem where any accident can take place, because K effective is less than, and therefore multiplication of neutrons will not go abruptly very high. So that is one area where these accelerators will play a very important role, and they will replace to a system which is inherently very safe. And for India, it is very important because we are having lot of thorium available in India, and so our fuel problem will be solved if we are successful in building those kind of accelerators, and as well as we are able to use them. Uh, that is one area where we are going to. Now, I will be very happy to answer any questions which particularly regarding about 8 lectures on DC accelerators first, and at the end we will have one more interaction session which will deal with the special lectures. One will be on laser plasma accelerators, and other one will be on ADS, accelerator driven subcritical systems. So today we will be discussing, we can discuss or clarify any doubts regarding DC accelerators, which are Cockcroft-Walton, Van de Graaff, tandem accelerators, peloton accelerators, and so on. So now I request the participants to ask if there is any doubt about these 8 lectures, which were dealing with these accelerators as well as some of the some components which are used in India. Basically, many labs have these DC accelerators, and they are maximum in the range of up to about 100 MeV, and the highest energy DC accelerators are, one is in the IUAC Delhi, that is with 16 million volt terminal, Peloton, and other one is at Tata Institute of Fundamental Research in Mumbai, that is 14 million volt DC accelerator. So they can give energy up to, in the case of heavy ions, they can give energies up to about 250 MeV maximum. And the limitation, of course, is that their currents are very small. When you go to pelotons, their currents are very small, while the currents in the case of Van de Graaff accelerators and Cockcroft-Walton type of things, they can be very high. High meaning not in several milliamperes, but they can be several hundred microamperes also. There are two accelerators which have been purchased recently. One is in uh, chains, and therefore the current can be high in that case. And another high current accelerator uh, operational at IIT Kanpur, and several other accelerators in the range of 3 MeV or so are in operation. There is a question how to determine the induced radioactivity in accelerator components after long-term operation. See, whether it is a long-term or short-term operation, the if the component is has become radioactive, you have to measure the activity. For example, suppose gamma activity is induced in that, then you have to put gamma detectors, and then you have to put it the gamma detectors and measure the radioactivity there. So in the accelerators, one should not go nearby without measuring the activity, because activity, radioactivity cannot be seen directly, and therefore you have to use the detectors and measure the radioactivity, and then you have to uh, you have to approach them. You have to go very close to them if the activity is less than the limit of that, and therefore one should not go very close to it unless. So this activity is generated only if beam is defocused and it hits the accelerator components, particularly the beam line. And if hits there, the activity is produced by nuclear reactions. And to measure that, you have to put a, for example, either particle detectors or particle detection detectors or gamma ray. Normally, in most of the cases, the activity induced is by gamma ray and gamma activity induced, and that should be first measured using the gamma ray detectors. That is how it is has to be done. Now you are saying that if in the case of operation, when the accelerator is in operation, that time what you do is that you put the detectors, you mount the detectors permanently there, and the connection is taken to the control room, and where the directly reading comes continuously there. So during long-term operation, the radioactivity is measured by installing the gamma ray or the any other detectors permanently there, which will keep monitoring the activity and keep giving the reading in the control room itself. No, I think we can switch over to questions if there are any questions from the participants regarding these first eight lectures on the accelerators. These eight lectures actually they were dealing normally with how the voltage is produced, how that voltage is created, and then see when once you know the voltage, then energy of the charged particle be can be calculated by multiplying the voltage to the charge, and then of course once you produce the voltage and which will give you energy, then you have to calculate the energy, or uh, you should also know whether that calculated energy is correct or not. That means you have to calibrate it, and uh, using that calibration you have to measure the energies. So calibration can involve the errors, and that error will be reflected into the energy, and therefore one has to be careful while you are calibrating it. And the third one, of course, is the energies. See, energy or the voltage will vary little bit, and therefore it has to be corrected to bring, because in all the nuclear reactions or even atomic reactions, the energy required is has energy has to be very accurate, and there you should know it that is very is correct, and therefore if the energy has changed slightly because of various reasons, for example, as I said, that energy is calculated from the volt, and voltage may vary because one of the source of variation of voltage is on any surface is corona spark. Suppose corona or leakage or spark is an extreme case of that, but corona leakage, and if suppose that corona is leaking, then you have to correct that, and you have to find out the correct energy of that. So corona control system has to be there, which will bring the energy to the prescribed value once again. Suppose the voltage has changed, then you have to correct that voltage again back to the uh, value, so that the energy again comes to the correct value. And of course, that this the question which has been asked. See, for example, if activity is produced and that is measured continuously. For example, if you take the gamma rays, gamma energy will also depend on the source energy. So this can be very indirectly, which is not used because that is quite tedious. Is that suppose you measure the radioactivity, and in radioactivity not only the intensity but also you can measure the energy of the gamma ray, which of course depends on the source energy. And if there is any change in the gamma ray energy of radioactivity, that means the energy of the particle which has induced that has also changed, and it should be corrected. So that is another way of, but this is not a correct way of doing it. It is not normally done. What is normally done is direct methods, which we have discussed in lectures. There are several methods which have been discussed, and they are much faster method. This will be a slow method. and but this can be one of the methods. Accelerator physics basically in the beginning, accelerator physics basically was a part of nuclear physics. But later on, as the accelerators grew, it has become a separate subject. But in the beginning, accelerators were developed for nuclear physics studies. For example, this Venn diagram, peloton, and all that, they are used for nuclear physics experiments only. So these accelerators, in general, are for nuclear physics, and they were for very long time. Accelerator physics was part of nuclear physics. You are right. In fact, initially the accelerators were developed by nuclear physicists for nuclear physics experiments. For example, Rutherford, etc. They developed the accelerators. Cockcroft, Walton, and many other, or Veldegraph. They were all nuclear physics people in the beginning, and they developed accelerators for their experiment. In fact, even before the accelerators, radioactive sources were used for experiments. But the problem in radioactive sources was that number one, the energies were fixed, so energy could not be varied, and secondly, the energy variation was not possible. See, for example, if you want to study the variation of cross section, for example, with the energy, then you cannot do there, because the any emission of particles or whatever, they were having the fixed energies, and that is why it was necessary that some source should be developed, some device should be developed which can give variable energy particles, and accelerators came into picture because of that. But you are right that how the in the beginning, accelerator physics was part of nuclear physics. In fact, I remember up to 70s or so, there used to be one chapter on accelerator physics or accelerator. In fact, that time there was not much of accelerator physics. It was only accelerators. So there used to be a chapter on accelerator in nuclear physics books. But later on, the importance of accelerators grew, and accelerators became independent, and now today accelerator is a subject by itself, and there are almost like 30 to 40,000 accelerators operating in the world today. And energies could be energies are from keV energy to TeV energies. There are TeV energies. For example, if you take CERN, uh, LSC, Large Hadron Collider, there 7 TeV protons collide with another 7 TeV protons. That way, in that CERN case, from both sides the proton beams are coming, opposite side, and they interact, and the center of mass, and because they are coming from the opposite side, and therefore their energy, center of mass energy, which is responsible for any nuclear reaction or any interaction to take place, becomes 7 plus 7, that means 14 TeV. So that kind of big accelerators have been built. There the LSC circumference is a circular rings, and the circumference is about 27 kilometers. Also going to build one more bigger accelerator, which is called FCC, which is a circulating ring, where the circumference is about 100 kilometers, roughly 100. Energy will be about 100 TeV. So in the sun, actually, it is two proton beam collide coming from the opposite side. Each one is having 7 TeV by 7 TeV. So the center of mass energy is 14 TeV. But for example, if you take Fermi Lab, there 1 TeV beam coming from one side, and from the other side, from the opposite side, anti-proton beam comes. So that is a proton and anti-proton kind of TeV beam is, let's say, coming from the left, and another 1 TeV beam will be coming from the right, and they will interact, and there will be, they study the proton and anti-proton beam reactions. See, in the case of DC accelerators, as I said, that energy resolution is very high. Uh, Energy resolution very high means the delta E is very small. So suppose you have 5 MeV beam, and the variation of different particles in that can be very small. So all the nuclear reactions which need very high resolution beam, they are studied using the DC accelerators. And DC accelerators are very useful for these nuclear reactions studies, and particularly when the different levels are very close to each other, you can identify them only if the beam resolution is very good, and that kind of that is done. And they can also be used, but they are not very useful in that case, because in the case of DC accelerators, the currents are small. Normally currents are small, they are in microamperes, normally few microamperes, and they cannot be very effectively used for isotope production. That is why for all the medical cases or the healthcare, for isotope production, normally cyclotrons are used. Low energy cyclotrons are used because they are the can be pretty large. That can be several hundred microamperes, or in some cases it could be milliampere also, one or two. But it cannot be very high. It cannot be several milliampere, because then the space charge becomes very prominent, and it is very difficult to contain the beam. At CERN, for example, when two proton beams were coming from opposite direction, they collided. Actually, it's not a physical collision; it's an interaction. And at about 5.7, actually 6.5 TeV energy center of mass, these Higgs bosons were produced, and they were discovered in 2012 or something. And now this new FCC project, which has been sanctioned now, is being will be used for uh, find out whether some more particles like Higgs bosons are available, and their interactions. Right now, they have been produced, but their interactions have not been studied because the intensities are low, and intensities will increase at higher the energy, and this FCC is being built for that purpose. There are several labs where these high energy accelerators are being built in Japan, CERN, Fermi Lab in the USA, and one more lab which is going to be very, very useful is that is that's a project fair in the Darmstadt GSI in Germany. Their beams of antiprotons and of different heavy, even heavy ions will be accelerated there, and the reactions will be studied there. So nowadays, see, when you are saying the frontier physics, now if you really look at it, then even today, in Physical Review Letters, which is the best journal for which publishes the discoveries, equal number of papers are published in that which are coming from low energy DC accelerators, because there, as I said, that energy resolution is very good, so very accurate measurements can be done. So it is not that only TV accelerators are good and DC accelerators are useless. It's not that. Each energies in the case of in each energy are equally important. So DC actually, in fact, very large number of papers are published even with the few hundred keV beams, because if you have an accelerator where keV beams are available, let's say 100 to 200 keV, but the energies could be large, then the lot of experiments can be done. Material done, and for example, I'll give you one example where they found that if you implant nitrogen on the tools which are used for grinding and all that, then the at certain level, certain flux and energy, the life of the uh, tip which is used for grinding increases by a factor of 5. See, if life increases by order of 5 times, then the cost of this whole thing will decrease 5 times less. The number of tools which will go bad, they will not so many tools will be required for that. So it has been found that if nitrogen is implanted on the tip of the tool which is used for grinding or cutting, then the life of that increases by a factor of 5. So like this, and that is done at very low energies, few hundred kVs. Secondly, for example, for neutron production, what you need is only few hundred kV. You don't need very high energies. And neutrons are required. For example, 14 MeV neutrons are required everywhere. So 14 MeV neutrons, as I shared in the first lecture itself, through DT reaction you can produce uh, D plus T going to helium 4 plus neutrons, and Q value is 17.6 MeV, and this reaction can be used for 14 MeV monoenergetic neutrons, which can be used in several applications. So uh, that can be done only at very low energies. So one should not think that these low energy things are not very important. They are equally important. They are equally useful. It's not that only 100 TeV beam or 10 TeV beam is the only one which is useful. They are useful for finding certain kind of experiment. For example, to create new particles. For example, at 7 TeV that Higgs boson is produced. Similarly, for if suppose the high energy particles are there, then some more particles can be produced, and that is what people are trying to do it. So in each kind of accelerators are useful depending upon the application. For example, if you take cyclotrons, now if you see more and more cyclotrons in the range of about 20 MBV or 30 MBV are sold, and they are being installed in various hospitals. Because if you take about for example, if you take one cyclotron which is 16.5 MBV, which is used for producing fluorine 18, which is used for diagnostics of the cancer, for cancer. So that is used almost like 24 hours. It is operated to produce fluorine 18. So fluorine 18 is used for beam this cancer diagnostics. And for example, 30 MBV cyclotrons can produce some more isotopes, which can be used for not only cancer but some other diseases also. So low energy accelerators are equally important. One should not get a feel that only very high energy accelerators are useful and low energy accelerators, because for example this FCC is going to cost, see the high energy accelerators, for example FCC is going to cost about 23 billion dollars, and now it cost must have gone up further. So high energy accelerators are very costly, not everybody can afford, and they are quite complicated also. So one should not think that only those accelerators are useful.
Hello, sir.
Yeah, yes, Priyanka ji.
Sir, I wanted to ask one question that in the first lecture, uh, it was told that uh, low energy accelerators are means like it has some applications and it has some applications in astrophysics also. So, can you
Yes.
tell what kind of like how it is used in astrophysics and about other applications also?
See, low energy accelerators are used roughly all the fields. For example, nuclear physics, I told. See, first Nobel Prize proton beam of about 700 keV was bombarded on lithium 7, and two helium nuclei were produced. And that was the first experiment done using Cockthroat-Walton type of accelerator, and people got Nobel Prize in 1951 for that. So that was a nuclear physics. So several nuclear physics can be experiments can be done. Experiment atomic physics can be done. Astrophysics, you mentioned one, astrophysics. Basically, they are all nuclear reaction studies, and you want to use, for example, the astrophysics. uh, Astrophysics, normally the cross sections are very low. So these reactions they study, they take a very long time, but it doesn't matter. Low, and most of these experiments are in the range of few hundred keV to few MBV maximum. So astrophysics experiment, they are all nuclear physics experiments, nuclear reaction studies. Astrophysics mainly is their cross sections are very low, and therefore you study. There are so many things which are done. See, nuclear reaction is one of them. Other thing, at low energy, I told you that if suppose you use ion implantation. Ion implantation means the one example I gave, that tip of the grinding tool. If you implant with nitrogen, the life of that goes by factor of 5. So that is another example. That is modification of material. Another, for example, low energy beams, which which is very useful for astrophysics, is beam foil spectroscopy. So many experiments are done in beamfoil spectroscopy, which are useful for astrophysics as well. Astrophysics is one is that, see, for example, if you take the spectrum of, let's say, a star or something, then you will like to know what is the percentage of each material in that: oxygen, protons, electrons, and all that. So, using beamfoil spectroscopy, you can find out the fraction of various elements in that source. So that is another way of beam foil spectroscopy. Doesn't need very high energies. It needs only few MeVs. Beam foil spectroscopy, I'm sure you know, you start with a beam, it passes through the foils, and for example, negative ions are changed to the positive ions, and then you study the certain labels, measure their half lives. Based on those half lives and other parameters, you find out the fraction of that element. And if the sample is coming, for example, if you must have heard it, that in the beginning, when the satellites were sent to the outer space, they brought the of moon and others sources, and those samples were studied in various labs for various applications, and beam foil spectroscopy was one of them. And from that, in the samples, we could know that what are the elements and what is the ratio of those elements. See, it will not be one element, but suppose there are several elements. You find out those elements, and then you see that what is the fraction of that element in which you are interested, and that study of those elements will depend upon the lifetime studies of various levels in that one, and those levels are excited in the beam foil spectroscopy experiments. So these are some of the examples. There are hundreds of examples which I can give, but these are few examples which are very commonly used. There are
Okay,
a
sir.
couple of for example, RM, this radio carbon dating is done through these small accelerators also. You know that carbon dating, carbon 14 by carbon 12 ratio is measured from this ratio is fixed, and carbon 14 is a radioactive, and carbon 12 is a element which is almost like it has very long life, while carbon 14 is having is about 5720 years. So using this ratio, one can find out what is the age of. See, for example, one of the studies which is mainly done, suppose there is a tree, and you want to know life of the tree is 1 million year old. Now you want to know what is the life. You in the beginning you don't know, so you do this carbon 14 ratio, carbon 14 to carbon 12 ratio, and from that you can find out what is the age of that tree, or you can find out the age of a mountain. There are various applications which can be that this field has grown now. In the beginning, it was a small field, but now it is an independent field that's called accelerator mass spectroscopy, AMS. AMS basically is done, carbon 14 by carbon 12 is the main thing which is done. But there are many other studies which are done now. For example, now one example I'll give that. See, for example, in reactors, minor actinides are produced. Radioactive waste is produced. Now, one of the problem there is that where to store that radioactive waste, and some of the elements of that radioactive waste, they have lifetime of several hundred years, thousands of years. Now that has to be put somewhere. Now suppose you dig a hole in the earth and put that one in a container, then maybe after 5,000 years or something, a earthquake comes that may this radioactivity may come out. So that is not a safe way of see. So one of the place where people are thinking, people have been doing a lot of R&D, is that they can put that minor actinides or radioactive waste in the containers and dump in the sea. And in the sea means under the sea there are very heavy currents. Now, so they want to find out, is there any place where there is a portion of the sea where the undercurrent is very small, or there's no, for millions of years the water has not moved. Now, if you can find place, then you will not move from there. Now, from that, to find out that place, there is a way. AMS can be used, and you can use, for example, chlorine 36, some isotopes. You can use ratio of this like carbon 14 to carbon 12. Similarly, you can use that chlorine 36 to argon 36 kind of things, and by the ratio you can find out for how long water has not moved from there, because by the decay etc nuclear reaction that you can find out the way the water has not moved for how long, millions of years. There the scale time scales is millions of years, and therefore you can this is one way that these low energy accelerators are very useful, very useful to find out these things. Now in fact I will make a sweeping statement that now these accelerators have become a almost like household thing. Small accelerators are available, and they are used in all the fields everywhere. There are at least hundreds of fields now growing up, and I think the field where it is making the biggest impact nowadays, which according to me is the healthcare. The accelerators are making tremendous uh, contribution to the healthcare of that, and that is because accelerators can be used for producing the isotopes which are of important to the medical fields, and they can easily be produced in the accelerators by nuclear reactions. And of course you have to separate out nuclear reaction means other things also will be produced. You can separate them out, and you can then use them in medical case. And now I heard that almost 30 to 40 accelerators are being set up in India for in various hospitals for medical applications and producing. So, see, if you want to produce only a fluorine 18, then even 16.5 MeV is enough. But if you want to produce isotopes of specs and other things, then for example, 30 to 40, 30 MBV is required minimum. You have to see the threshold. And then now accelerators with 30 to 35 MBV are also being set up, and isotopes are being produced. So that is one thing. Of course, I can count almost 10 to 15 fields where these accelerators are playing. But at this moment, I would like to just add that initially the accelerators were developed for nuclear reactions, nuclear physics. They were part of the nuclear physics, and all in the beginning, if you see all nuclear physics people, all the accelerators were developed by nuclear physics people in the beginning. But later on, of course, it became a separate field, and today it is not only accelerator development but also accelerator physics. Because, see, once you are dealing with high currents, then you have to understand the beam trajectories, beam dynamics, and everything. Otherwise, if well, high currents are involved with reactive, for example, in the case of ADS, even the current hits the component, it will make approach the component for maintenance or any purpose, and therefore you have to be very careful. And that is why in one site, when the current involved is very small, that time you can do the that particle trajectory calculations are no more useful. You phase charge effects have to taken in account, and then that time you have to worry about the phase space or the emittance growth. So you have to do the calculations, the emittance growth progresses, and the space charge has to be the equation plus equation valid only for low high currents are involved, then you have solve the Poisson sequence, and space charge has to be taken into account. And at that time, instead of just calculating the coordinates x and y of the particle, to calculate the bunch of beam, and you have the emittance and